Z-Wave is a wireless communications protocol designed for home automation, specifically for remote control applications in residential and light commercial environments. The technology uses a low-power RF radio embedded or retrofitted into electronic devices and systems, such as lighting, access controls, entertainment systems and household appliances. Overview: Z-Wave communicates using a low-power wireless technology designed specifically for remote control applications. The Z-Wave wireless protocol is optimized for reliable, low-latency communication of small data packets with data rates up to 100 kbps, unlike Wi-Fi and other IEEE 802.11-based wireless LAN systems that are designed primarily for high-bandwidth data flow. Z-Wave operates in the sub-gigahertz frequency range, around 900 MHz. This band competes with some cordless telephones and other consumer electronics devices, but avoids interference with Wi-Fi, Bluetooth and other systems that operate on the crowded 2.4 GHz band. Z-Wave is designed to be easily embedded in consumer electronics products, including battery-operated devices such as remote controls, smoke alarms and security sensors. Z-Wave was developed by a Danish startup called Zensys that was acquired by Sigma Designs in 2008. As of 2014, Z-Wave is supported by over 250 manufacturers worldwide and appears in a broad range of consumer and commercial products in the US, Europe and Asia. The lower layers, MAC and PHY, are described by ITU-TG 9959 and fully backwards compatible. The Z-Wave transceiver chips are supplied by Sigma Designs and Mitsumi. Some Z-Wave product vendors have open-source options for the hobbyist communities. They require users to start with a complete Z-Wave transceiver from a Z-Wave OEM such as an Intermatic USB stick. The XPL project also provides open-source support for Z-Wave products, but requires Microsoft Windows. Since 2010, there has been a project called OpenZWave that seeks to offer development support without expensive software development kits. Another project has created a Z-Wave daughter board for the Raspberry Pi, a credit card-sized single-board computer. Z-Wave is a protocol oriented to the residential control and automation market. Conceptually, Z-Wave is intended to provide a simple yet reliable method to wirelessly control lights and appliances in a house. To meet these design parameters, the Zens or Sigma Design Z-Wave package includes a chip with a low data rate that offers reliable data delivery along with simplicity and flexibility. Z-Wave works in the industrial, scientific, and medical band on a single frequency using frequency shift keying radio. The throughput is up to 100 kbits and suitable for control and sensor applications. Each Z-Wave network may include up to 232 nodes, and consists of two sets of nodes, controllers and slave devices. Nodes may be configured to retransmit the message in order to guarantee connectivity in the multipath environment of a residential house. Average communication range between two nodes is 30.5 am, and with message ability to hop up to 4 times between nodes, this gives enough coverage for most residential houses. Z-Wave Alliance. The Z-Wave Alliance is a consortium of over 250 independent manufacturers as of 2014, who have agreed to build wireless home control products based on the Z-Wave standard. Principal members include ADT, GE Jasco, Evolve, Ingersoll Rand, Linear, FAKRO and Sigma Designs. As of 2014, there are more than 1,100 different products certified by the Z-Wave Alliance. Products and applications from the Z-Wave Alliance span all major market sectors for residential and light commercial control applications. These include lighting, HVAC and security control, as well as home theaters, automated window treatments, pool and spa controls, garage and access controls and more. Radio specifications, bandwidth, 9600 bits, 40 kbits or 100 kbits. Speeds are fully interoperable. Modulation, GFSK Manchester channel encoding, range, approximately 100 AFT assuming open air conditions, with reduced range indoors depending on building materials, frequency band, The Z-Wave radio uses the 868.42 MHz SRD band. The 900 MHz ISM band, 908.42 MHz. 916 MHz. 919.82 MHz. 921.42 MHz, India 865.2 MHz. Z-Wave units can operate in power-save mode and only be active 0.1% of the time, thus reducing power consumption substantially. Z-Wave network setup. Z-Wave utilizes a mesh network architecture, and can begin with a single controllable device and a controller. Additional devices can be added at any time, as can multiple controllers, including traditional handheld controllers, key fob controllers, wall switch controllers and PC applications designed for management and control of a Z-Wave network. A device must be included to the Z-Wave network before it can be controlled via Z-Wave. This process is usually achieved by pressing a sequence of buttons on the controller and on the device being added to the network. This sequence only needs to be performed once, after which the device is always recognized by the controller. Devices can be removed from the Z-Wave network by a similar process of button strokes. This inclusion process is repeated for each device in the system. The controller learns the signal strength between the devices during the inclusion process, thus the architecture expects the devices to be in their intended final location before they are added to the system. Typically, the controller has a small internal battery backup, allowing it to be unplugged temporarily and taken to the location of a new device for pairing. The controller is then returned to its normal location and reconnected. Topology and routing. Each Z-Wave network is identified by a network ID, and each device is further identified by a node ID. The network ID is the common identification of all nodes belonging to one logical Z-Wave network. The network ID has a length of 4 bytes and is assigned to each device by the primary controller when the device is included into the network. Nodes with different network ID unregistered trademark S cannot communicate with each other. The node ID is the address of a single node in the network. The node ID has a length of 1 byte. It is not allowed to have two nodes with identical node ID on a network. Z-Wave uses a source-routed mesh network topology, and has one primary controller and 0 or more secondary controllers that control routing and security. Devices can communicate to one another by using intermediate nodes to actively route around and circumvent household obstacles or radio dead spots that might occur. A message from node A to node C can be successfully delivered even if the two nodes are not within range, providing that a third node B can communicate with nodes A and C. If the preferred route is unavailable, the message originator will attempt other routes until a path is found to the C node. Therefore, a Z-Wave network can span much farther than the radio range of a single unit. However, with several of these hops a slight delay may be introduced between the control command and the desired result. In order for Z-Wave units to be able to route unsolicited messages, they cannot be in sleep mode. Therefore, battery-operated devices are not designed as repeater units. A Z-Wave network can consist of up to 232 devices, with the option of bridging networks if more devices are required. As a source-routed static network, Z-Wave assumes that all devices in the network remain in their original detected position. Mobile devices, such as remote controls, are therefore excluded from routing. In later versions of Z-Wave, new network discovery mechanisms were introduced. So-called explorer frames can be used to heal broken routes caused by devices that have been moved or removed. Explorer frames are broadcast with a pruning algorithm and are therefore supposed to reach the target device, even without further topology knowledge by the transmitter. Explorer frames are used as a last option by the sending device when all other routing attempts have failed. See also, 6 Low WPAN a Euro IPv6 based automation network, DASH7 a Euro active RFID standard, N-Ocean a Euro low power, typically battery-less, proprietary wireless technology, Insteon a Euro dual mesh technology, Myrianet a Euro low power, biology-inspired, wireless technology, 1net, a Euro open source standard for wireless networking. OSIAN, a Euro open source IPv6 automation network. X10, a Euro, one of the earliest popular home automation systems. Zigbee, a Euro standards-based protocol based on IEEE 802.15.4. Thread, standard suggested by Nest Labs based on IEEE 802.15.4 and 6 low WPAN. Bluetooth Low Energy, Ultra Low Energy version of Bluetooth, Taboo Mac, a custom Mac layer, developed for use in Ultra Low Energy WSN. References. External links, official website, Z-Wave Alliance, open consortium of over 250 manufacturers of Z-Wave products, Open Z-Wave project.